Good day, students. You are welcome to today's lecture video on spectrophotometry. In these lectures, we will be explaining the basic principle behind spectrophotometry, and also we are going to answer some exercise questions so that it will aid your understanding of the practicals, as well as guide you on how to report so that you have maximum marks at the end of the day. So what is spectrophotometry? It is the base word is spectroscopy, and spectroscopy is the study of how light interacts with matter. That's simply what spectroscopy means. And spectrophotometry is the measurement of the interaction of light and matter. So the interaction of matter and light is spectroscopy. So the measurement of that interaction is what spectrophotometry is all about. It is a method that is used to measure how a chemical substance absorbs light by measuring the intensity of light as a beam of light passes through the sample or solution. And the basic principle is that each compound can absorb light or transmit it over a certain range of wavelengths. For example, nucleic acid, they absorb light at a certain region maximally because of the constituent of that nucleic acid. You are talking about purine bases or pyrimidine bases that they have what ring structure, which is alternating pi electrons that is resonating that will make it to absorb light. And they absorb light at a region of 260 nanometer. That's their region of maximum absorption. If you look at protein also, they can absorb due to the presence of aromatic amino acid, tyrosine, phenylalanine, and tryptophan, and so on. So due to the presence of such aromatic ring that is present in the aromatic amino acid, proteins can absorb light also. They can absorb light at a region of 280 nanometer. So some solutions cannot absorb light. For example, sugar solution, a solution of glucose, they cannot absorb light. And the basis for that is that you can, for a solution that do not absorb light, you can actually form a mixture of a solution that can absorb light and a solution that do not absorb light, so that you make it in such a way that you have an absorption, so that you form an absorption spectrum of that substance, so that at the end of the day you can deduce the concentration and quantify that substance at the end of the day. So if you look at this picture, this diagram is trying to explain how the spectrophotometer works. You have a light source that is passing through a lens, which is collimator, and you have a monochromator, which usually is prism or grating that will help in focusing the light on the slit, which is the wavelength selector. So now, as the light is passing, you can see that what is seen here is what we call the incident light, and you have your now sample inside your cuvette or cell inside the spectrophotometer. This sample is the sample that you want to measure the absorbance of that sample. So this incident light will fall and pass through the solution, and you have what we call the emergent light. As you can see, this substance is the concentration of the substances that or the solute that is found in this solution will now absorb light. So the more the substance or the solute concentration, the higher the light that will be absorbed, and the lower the light that will be transmitted. So you have now a photo cell or a detector that will now transmit that signal that you receive from the solution, and you have your digital display as your output, the absorbance that is being displayed. So if we look at this diagram tries to explain the principle behind how some substance absorb colored solution at certain wavelength and selectively absorb the resultant color that is being transmitted. So what basically this diagram is going to explain is that when a light passes through a colored solution, you know that certain wavelengths of light are selectively absorbed, and the resultant color is due to the light which is transmitted. So in biochemistry, there are a lot of measurement that is taking place, and the measurement of measuring the light absorbed by solution of substance in a solution in the visible or ultraviolet region of electromagnetic spectrum. Usually, we use photometry or spectrophotometry to do that measurement. So for a red substance or a red solution will absorb light maximally at a region opposite to it, which is at a region of green. So it's important you understand this diagram. So also a green solution will absorb light maximally at a region opposite to it, which is red. So also purple will absorb maximally at a region opposite to it, which is yellow. So also yellow at a region opposite to it, which is purple, orange at a region opposite to it, which is blue, and blue at a region opposite to it, which is orange. So you've already carried out this practical. You have seen the different wavelengths that you turn from the L spectra, and you have observed the corresponding light that is absorbed by the solution in the region that is opposite to it. And I believe you understood that because you have carried out the practical. So what is actually governing the measurement of this light? We have two laws that govern the measurement of this light. We have the Lambert's law and the Beer's law, which they jointly together to form Beer-Lambert's law. So when for Beer's law, for Lambert's law, it states that when a ray of monochromatic light, when we say monochromatic light, is a light of single wavelength. When a ray of monochromatic light passes through an absorbing medium, its intensity decreases exponentially as the length of the absorbing medium increases. So when light is passing through an absorbing medium, the intensity of that light decreases with the length of that medium that the absorbing molecule is being placed in it. And this is the expression I, which is the incident light, is equals to I, which is the emergent light, is equals to incident light, which is I naught exponential K multiplied by L, where K is constant and L is the path length. So we are going to come back to this calculation to see how we can drive the Beer and Lambert's law equation. So at the end, we actually not in this video, but we'll come back to do a simple derivation of how we can see at the end of the day, we arrive at the Beer-Lambert's law. So for Beer's law, it states that light absorption is directly proportional to the path length and the concentration of the solution, which is given by this expression. Absorbance of light, right, is equals to molar extinction coefficient times path length times the concentration. So this is a diagram showing that this is a beam of light pass is shown through a solution. The absorbance that is obtained from the readings in the spectrophotometer is directly proportional to the path length, the molar extinction coefficient, and also the concentration of the absorbing molecule. So jointly together, we have Beer-Lambert's law, which says the absorbance is directly proportional to concentration of the solution. So absorbance is proportional to E, is directly proportional to concentration and path length. So this E is constant. Molar extinction coefficient for each substance or solution, they have their own molar extinction coefficient, which is also equivalent to log I naught over I, where C is the concentration in molar, which is mole per liter, L path length of light through the cell, which is 1 centimeter cell, and molar absorption coefficient, which is liter per mole per centimeter, or per molar per centimeter. So, and this is basically what we earlier explained, that you have a source of light passing through a monochromato, and you have an incident light that passes through the cell or the cuvette, and the light I, which is the emergent light, is being transmitted, and you have a detector in the spectrophotometer, and you have your digital display at the end of the day in form of absorbance. And that absorbance, actually, you can use it to calculate the concentration. If you are given an unknown sample, you can calculate the concentration of that solution after taking the absorbance. So let's look at these two equipment that are used in spectrophotometry. We have the colorimeter and spectrophotometer. So what is a colorimeter? They are the colorimeter and spectrophotometer. They are the equipment that are used in colorimetry and spectrophotometry respectively. So there are some students that usually mistake colorimetry and calorimetry. Calorimetry is measurement of heat, okay, while colorimetry is measurement of color solution, a solution. Okay, so you should not mix up the two while writing. If you write CA, is calorimetry or calorimeter, okay? So it's now CO, colorimetry. Please take note of that. So for spectrophotometer, for spectrophotometry and colorimetry, there are techniques which can be used to identify molecules depending on their absorption and emission properties. This is an easy technique to determine the concentration of a sample which has color. You remember some substance can absorb light and some they have color, while others are colorless. And for you to measure their concentration, you have to mix them together with a substance that is known for its color, and you mix it together and you extrapolate the concentration of the other one that is not colored. We will see examples, because in these practicals all through they are linked together. After this, the next practical you are going to do practical on preparation and uses of standard curve, and before that you will do absorption spectrum. So it's easier to understand absorption spectrum if you really understand the spectrophotometry and colorimetry. So this is a colorimeter and this is a spectrophotometer. They have differences, but we are going to look at colorimeter first. Then we'll talk about spectrophotometer briefly. Then we'll look at their differences. There are few parts that are common to any colorimeter. We have a light source, which is normally a low filament lamp that is used in the colorimeter. Also, we have a set of color filters that are there. And also, according to the sample we are using, we can choose to require a filter. A sample is placed in a cuvette. A cuvette is the cell. You have already seen it in the lab. It's the cell or the container that you put your sample before inserting it into the colorimeter or spectrophotometer. There is also a detector that measures the transmitted lights, and also there is a digital or analog meter to display the output in form of what we call absorbance. So also spectrophotometer, They are designed to measure the absorption, and they compose of a light source. Also, they have light source, they have a wavelength selector, and they have a cuvette and also a detector. So wavelength selector only permit the selected wavelength to pass through the sample, because for each sample, for each colored solution, it has its own wavelength of what maximum absorption. So there are different types of spectrophotometers. We have UV visible, we have FTIR, we have atomic absorption spectrophotometer, and etc. So what's their differences now? What is the difference between colorimeter and spectrophotometer? The colorimeter quantifies color by measuring three primary color components of light, that is red, green, and blue, whereas spectrophotometer measures the precise color in the human visible wavelength. Colorimetry uses a fixed wavelength, which is in the visible range only, but spectrophotometry can use wavelength in a wider region, such as the UV and also the infrared. Colorimeter measures the absorbance of light, whereas the spectrophotometer measures the amount of light that passes through the solution. Please, you should take note of the differences between the two. So let's look at absorption spectrum. Absorption spectrum. When we say absorption spectrum, we mean it's a graph or diagram that is showing the relationship between absorbance and wavelength of a solution of a specified composition. So here, basically, what we are looking at is when you are asked to plot an absorption spectrum, because each solution, they have their own, each solution that can absorb light, there is a region where it can absorb light maximally. So we're talking about absorbance and also the wavelength of that particular absorption, where that particular absorption take place. So many compounds, they have characteristic absorption spectra in the ultraviolet and visible regions, and identification of these substances in a mixture is feasible, is very possible. It's possible to identify these substances. Now, for example, we know proteins, as I earlier explained, they can absorb strongly at 280 nanometer due to the three types of its constituent amino acid. For example, here we have aromatic amino acid here. You can see phenylalanine tyrosine, right? They are the ones that make the absorption feasible, and the wavelength at which this maximum absorption occurs is at 280 nanometer. Look at the peak for tryptophan, look at the peak for tyrosine, and look at the peak for histidine. Okay, so also we have nucleic acid, which they absorb basically at a region between 240 to 70 nanometer, but the absorption peak, the region where nucleic acid absorb light maximally, is at a region of 260 nanometer. So for protein is 280 nanometer, while for nucleic acid is 260 nanometer. Take notes, we can ask questions from this, and so you should be able to answer it. So why is it that protein absorb strongly? Is because of what aromatic nature of the amino acids, aromatic amino acids that are found, right? So why is it nucleic acid absorbed? Is because of the transmission of an aromatic nature of their bases. That is what ATGC, adenine, thymine, guanine, cytosine, and uracil also. Okay, so if you look at this absorption spectrum, is absorbance on y-axis, look at it, absorbance on y-axis, and wavelength in nanometer. Don't forget, whenever you are plotting a graph, you need to label it very well, the axis and their units, and give it a title. So wavelength in nanometer. So also we have, this is absorbance. The previous two graphs are absorbance for protein and nucleic acid, absorption spectrum for protein and nucleic acids. We also have some coenzyme, some coenzyme that can also strongly absorb light at a region of 340 nanometer. So we can say that the reduced coenzyme NADH and NADPH also, they absorb light strongly at a region of 340 nanometer, while their oxidized form, take note, it is the reduced form that absorbs light at 340 nanometer, while the oxidized form does not absorb. You should take note of that. So for NADH and NADPH, they absorb light at 240 nanometer, while their corresponding oxidized form NADP and NAD show no absorbance. Look at the here, look at it, it's flat straight line. So also here it's flat straight lines. Take note of that, please. So now let's look at the exercise that you are supposed to answer. Let's quickly look at it. This I just answer. Let's look at it and we answer it quickly. So in order to find, this is question 1, in order to find the exact absorbance maximum, that is the wavelength at which light is most strongly absorbed, that's absorption maximum, a 0.05% solution of an intensely colored drug was prepared and the absorbance was measured at a number of wavelengths in a 1 centimeter cell or cuvette. When we say 0.05%, we mean that 0.05 gram of that solution is weighed and dissolved in 100 mils of the solution, or is weighed, dissolved, and top up to 100 mils the solution. So this is the absorbance that is given. This is absorbance in wavelength in the nanometer, and also this is the absorbance that is given, the corresponding absorbance at 400 wavelength. We have an absorbance of 0.34. So also up to 500 nanometer, which we have 0 absorbance. So what you are going to basically do here, you are to plot a graph of absorbance as graph of absorbance as ordinate, which is the x-axis, against the wavelength, which is the abscissa, and that is the x-axis. So a plot of absorbance against wavelength, absorbance on the y-axis and wavelength on the x-axis. So this graph is called absorption spectrum. We define it as a graph of absorbance against wavelength. So you are going to look at the graph. From the graph, you look at the highest peak you have. What is the wavelength of maximum absorption? So where a region where you have that high peak, look at it. If it is something like this where you have high peak, you trace down to the wavelength axis and look at what is the wavelength there. That will be the maximum absorption for your graph or for that particular solution. So we are going to be needing graph to do that. So in this question, we have a question here that follows that says, what will be the absorbance of a solution of the drug Z of a concentration 1%? 1% is 1 gram in 100 mils. What 1 gram dissolve and top up to 100 mils at this wavelength, assuming Beer's law is obeyed. So what will be the absorbance of a solution of the drug Z of a concentration 1% at this wavelength, assuming Beer's law is obeyed? You should take note that this value that we are going to obtain is called the E1% 1 centimeter. That's a molar extinction coefficient, 1% 1 centimeter. It is the extinction, which is an old-fashioned word for absorbance, which is extinction of a solution of concentration 1% in a 1 centimeter cell at a stated wavelength. So in question 3, we are going to calculate the extinction 1% 1 centimeter, and also molar extinction coefficient of the drug Z, given that the molar weight of the drug is 400 grams per mole. So let's look at this solution. Now for that question that asks us to plot a graph absorption spectrum, you can see we have already plotted our absorbance on the y-axis, right? We have our absorbance on the y-axis. If you go back to the graph, to the data where you have the absorbance, look at it. You have up to 0.6 and you started from 0. So you should be able to have a good scale so that it span between the values, so that you have a good points. So you have absorbance against the wavelength. You can choose to start from anything above 350, so that you will not have a skewed graph to one side. Okay, you cannot start from 0 in the wavelength axis. Okay, so we started from 380 up to 500. So these are our points that we join. You use freehand sketch to join. Okay, so the region where you have maximum absorption, look at where you have maximum absorption. So you trace down and see what is the wavelength, what will be the wavelength there. Okay, look at it between 420 and 440. So if you go back to your graph, you will see, if you go back to the values that you have, okay, that value falls between what? That falls between 420 and 440. The highest absorbance here is 0.63. So 0.63 is the highest absorbance, and the wavelength of maximum absorption, or absorption maxima, is what we call the absorption where we have the highest the absorbance value where we have the wavelength where we have the highest absorbance, which is 430 nanometer. So that will be our answer for that. So the wavelength of maximum absorption is 430 nanometer. For question 2, we said that the absorbance of 0.1% solution from the table below, you know, you were giving absorbance. Look at this table. You are giving absorbance. You are giving a solution of blue solution, 3 different concentrations: 0.1, 0.05, 0.0025, and you have measured the absorbance at 650 nanometer. You remember? So the absorbance that you have, which one is the highest concentration here is 0.1. So you take that absorbance of that 0.1 and do the calculation of this question. So the absorbance of 0.1% solution from the table that you have taken the absorbance is equals to 0.03, 0.08. So what will be the absorbance of 1% solution, which is now going to be X? So you do mole concept. If 0.1% is having 0.08 absorbance, so 1% will have X, so that your X will be 1 times 0.08 divided by 0.1, which is 0.8. So for question 3, that asks us to calculate the molar extinction coefficient. Also, we can say for 1% of Z contains, it was given in the question that it is 1 gram in 100 mils. So 10 grams will be present in 1000 mils. So because 1 gram is in 100 mils, so how many grams will be in 1000 mils? When you do the calculation, you see that it's 10 grams. So molar weight was given as 400 grams per mole, and there is this formula that you can use. Molar concentration is equals to mass concentration all over molar mass, and this 10 gram in 1000 mil is the word molar is the mass concentration, which is in gram per dm cube per liter, right? So you have 10 over, and the molar mass in gram per mole, you have 400 gram per mole. So 10 divided by 400, which is going to be 0.025 molar. That will be the molar concentration. But you are looking for the absorbance molar extinction coefficient. So you use this expression: absorbance is equal to molar extinction coefficient times concentration times the path length. You already have the absorbance, which is 0.8, and you have your concentration 0.25, and your path length is always 1. So when you take the you make molar extinction coefficient as your subject of the formula, you have 0.8, which is absorbance over CL, 0.8 divided by 0.025 times 1, which you have 32 per molar per centimeter. So this is a brief explanation of what you are going to do, and I hope you really enjoy it. Thank you for watching. See you next